Thank you, Gav. Over to you, Roland, if you want to get things started for us.
So good morning. We understand there is an air quality problem. Everybody here is probably aware of some of the challenges, some of the regulations that we are trying to meet, but also some of the human costs and economic costs behind that. So let's start with that human cost of 4 million deaths at least across the world. Over 90% of the world's children exposed to poor air quality. It's been defined as the biggest environmental health challenge of this century. Very closely linked to some of our climate challenges in terms of the emissions, the atmospheric interactions of human activity, but much more tangible and immediate impacts for air quality, where people's health is impacted on a very tight timescale. A potential 5 trillion economic cost across the world. Having people unhealthy is expensive. It's not just the sort of personal impact, it's the social impact, it's the economic impact. There's the health service, there's the economic output, and there's that fundamental productivity challenge by people not breathing good, healthy air. We're starting to understand more and more about some of the health impacts of pollution, whether that's 29% of lung cancer that has been linked to poor air quality, whether that's dementia, diabetes, COPD, and as in the case of Ella, which we're probably all quite familiar with, a serious asthma attack, really linked to the spatial and temporal distribution of pollution. So the fact that certain roads were more polluted on certain days has been now legally linked to her death and the cause of her death. And again, it's a very tragic case, but one we need to learn from in terms of how we can manage that situation better, how we can minimize those peaks of pollution in areas where people might be exposed, but also how we can help that personal decision making, that personal information, where people are aware of health impacts. How do we get information to them so they can make their own decisions and ideally change outcomes in cases like this? Next slide, please, Greg. So we have an air quality challenge, and we have an environmental cleaning activity we need to get on with, and transport is one key aspect of that. There are a number of contributing factors, from agriculture to background dust to industrial outputs, but in most urban settings the transport contribution is about 70% of the NO2 and perhaps about 30% of PM 2.5. If you're living by a relatively major road in the city, that 70% can quite easily be above 90%. So the NO2, which is a key regulatory target and it's a key angle on human health, is really dominated by how we use our transport system, how we manage our fleet, and how we manage our human interaction with the emissions from that fleet. We're now starting to see an increasing amount of policies that are targeted at mobility and improving the way that we manage that transport system, and we manage the emissions from it, from the 2030 target in the UK and elsewhere, to try and remove the most polluting personal vehicles from the road, but also about how we understand how those emissions need to be tailored to protect human health as best we can, given the technologies, the fleet, the economics, and the legacy systems we have as part of our infrastructure. Next slide, please, Greg. So one quick slide on Earthsense before we really focus on the transport. Earthsense is an air quality company. We were spun out about 5 years ago with a set of technologies that we really wanted to apply to improve smart cities, urban environments, and operational management systems. So we have a technology for monitoring. We have the Zephyr air quality sensor that sits on street furniture. It sits as part of an integrated solution and monitors NO2, PM 2.5, among a range of other things. We have a model as well, which has full fluid dynamics, so it takes in all of the buildings and the urban topography, and it understands how the emissions in that environment are then ventilated, how they evolve over time, how they are distributed downwind, and then how they are impacting the population in that environment. So that modelling solution integrates our measurements and then passes out information to various other systems. It also enables us to do 3-day forecasting at 10-metre resolution in a city environment. And then finally, we have various web portals, web apps, APIs to get that data, whether it's in a visualized form for purely air quality information, or whether it's as a part of a reactive system that enables that information to drive other decision making and other portals and information systems for other applications. So that's an introduction to the challenge today, the air quality challenge in urban environments, and some of the technologies that Earthsense are bringing to the table to enable better mobility and cleaner transport systems as a whole. Thank you.
Thank you, Roland. Over to you, Gary.
Okay, so Roland's quite neatly described there, I think, the challenge that we currently see with air quality in our towns and cities. What we'd like to do now is sort of demonstrate how we are addressing that challenge, how we're looking to solve that challenge. And again, as he's just neatly described, a significant proportion of the poor air quality that we suffer in towns and cities comes from the vehicles that drive around that area. Maybe we should be looking at a link between how we use air quality monitors to influence traffic. So what we've done here is we've worked with our partners at Earthsense and the Zephyr model, and we've created what we call a Zephyr S, which is essentially a smaller version of the Zephyr. It's about a third smaller than the Zephyr unit. The existing Zephyr unit is usually mounted on a lamp column with solar panels, and so it has a battery compartment within the unit. What we've done is said, well, if we can integrate that sensor into traffic signal installations, we no longer need that battery unit. We can take power directly from the traffic signal controller. So part of the work under the NEVFMA project was to develop an integrated solution that allows these Zephyr units to be very quickly and easily connected to a traffic signal installation. And to do that, we developed two versions of a power supply that sit either inside an LV controller or an ELV controller of any manufacturer. We've got various pole mounting options for the Zephyr using a TAM torque of various sizes, so we can put it on any size pole. It's initially designed for the 114 normal pole, but we can go from that all the way up to the sort of diameters that you get for lamp columns. And the Zephyr can now be very, very quickly and easily deployed with minimal on-street work, assuming that you have spare cores at your pole cap. It's a very simple installation of being able to wire into that pole cap and then install the power supply inside that controller. So that's the physical integration that we've done to try and make these as easily deployable as possible within that transport setting. But we also need to be able to use that data. Crucially, having the sensors is not enough. We need to be able to use the data produced from that sensor within our traffic management strategies. So what we've done there is we've created or we've taken the API available from Earthsense MyAir platform, and that comes straight into Stratos. The data from the Zephyr goes into the MyAir platform initially to be calibrated and validated to make sure we're getting the absolute best measurements that we can from that unit. And then that validated data is taken through that API and then sits within the traffic management platform. And then in that traffic management platform, we have it's visualized in the environmental module. The data from the environmental module can then be used to trigger traffic management strategies. So what you now have the ability to do as a local authority is not only collect that data, but use it to be able to create a trigger that says perhaps if air quality reaches a certain threshold, you implement some form of strategy that hopefully would combat that poorer air quality and improve the situation out on street. So basically, it's a real sort of neat way of being able to get these sensors out at mass if possible, but actually crucially use that data. If we move to the next screen, Greg. We just have here a visual of how that data is presented in Stratos for the traffic manager. So it all comes across the API, as we said, and it's tabulated, as you can see on the top right. On the left, we have a map showing the position of all the sensors and the health of all the sensors. And then if you were to select a particular sensor and a particular gas or particulate you wanted to visualize from that sensor, on the bottom right there, you can see the data is then graphed. So it's very easy to see at what point of the day or which day you're having hotspots of increased poorer air quality that you're able to then deal with as a traffic manager if it's traffic related that's causing that particular problem. So that's how we've integrated the service and the data provided from the Zephyr all the way into a traffic management system for a traffic manager to be able to make meaningful interventions and hopefully improve the situation in towns and cities. Over to Gav, explain a bit more about the NEVFMA project.
Thanks, Gary. Yeah, so Aimsun was the project lead for NEVFMA project. It started in 2019, September 2019, and ran through until November 2020. Originally, it was a 12-month project, but it's actually carried on for 15 months, partly due to the COVID situation. Aimsun, we're a traffic modelling software company. We provide offline and online software. And the reason to explain that is that first off, when we're looking at the consideration between traffic modelling and air quality and the road network, well, we start with an offline model. Traditionally, there are static models, regional models that cover a whole large area, but they really just have one view of a 3-hour period in the morning, perhaps a 3-hour period in the afternoon. So they don't really have the details of the dynamic nature of the peak period, the AM, the 8 o'clock to 9 o'clock. They don't really have that curve as the traffic ramps up before it just gradually goes down as people get to the offices. So our first part in phase 1 was to take the existing origin destination matrix of the county-wide model that existed in Oxfordshire and to basically upgrade that into our software and to create a dynamic model across the county. We focused on the green area that you can see, which is basically the Oxford city centre out to the ring road, but also the strategic road network. So the A34, the M40 and the A40 going into Oxford as well. So that model is effectively updated to 2019 standards. It's got a view of the network every 15 minutes, and it's very rich in its data. So it has it's then connected to all the various different systems that are out on the street. So I'll explain that on another slide. The model is using historical data. So we have the richness of the last couple of years of data and understanding traffic flows, and then we connect it to real-time data to get the real-time position and the real data that's flowing on the network at any particular time. And from that, we then take and consider the different traffic profiles, or what we call patterns, across the network. And basically, through clustering analysis, we can start to understand the differences or the different type of aspects of the flow around the network. And from that, we streamline that to get a set amount of patterns that basically can describe the conditions on the road network for 365 days of the year. So in this project, there's 10 patterns, and one of them is actually a COVID pattern because traffic was so different from the normal. And those 10 patterns effectively describe that network traffic on all situations 7 days a week. From that, we then use the tailpipe emissions element that we have in our software, and I'll explain the details behind that in the next slide. And we then pushed the tailpipe emissions estimates based on historic and current flow into the dispersion model that Earthsense produced. Next slide, please. So there's a little bit of lag with Teams when you swap slides before it shows on your own screen. So the tailpipe emissions we use is a London's emissions model. So it's a research model that was integrated by ITS Leeds in 2017. So it's a calibrated model using real vehicle characteristics, and so therefore it's quite accurate. When you're doing something like this, and I'll explain the actual architecture in a couple of slides' time, it's really important to understand the level of detail versus the trade-off against time. We're trying to work in a very quick period. But those LEM emissions estimates are sent to MapAir, and then in the MapAir system, we add that to the wind, the topographical data, the weather data, to get a true understanding of traffic flow in the air quality. And I'll show that for a couple of case studies in a little bit later. Next slide, please, Greg. So this slide shows emissions versus Zephyr versus MapAir, because what we want to understand is we've got 3 different ways of looking at the data. So we've got the tailpipe emissions in LEM, so that's the NOx that we're currently looking at, that's in the dark red. So this shows you the ebb and flow of tailpipe emissions over that period. We then have the Zephyr observed data. So what we did is we took one specific location just to show you this analysis. So this was Littlemore Roundabout. So this is the traffic flow over Littlemore Roundabout. This is the Zephyr, which is number 402 at Roundabout. So this shows you the observed air quality at that particular location. And then we have the dispersion model area, again at the same location. So what this graph shows you is that whilst we're looking at three different things, do they actually relate to each other? Can we see that there is a relationship between the tailpipe to the observed to the dispersion? And actually, it does show you that this is that there is a correlation, if that makes sense. What you'll see at the start of this particular period, we had some higher peaks, or we had some higher deviation between the three different data sets. But through calibration and training of the data set as we went over time, we started to tighten that down as the scaling factor came closer in reality. So we're really quite pleased that our system, from a traffic model with real-time data all the way through to the end of a dispersion model, could actually give us some meaningful data. Let's explain the system's architecture in the next slide. So we started off with that real-time information. So we've got the NIS system and the Network Information System from Highways England. So this is all Highways England's traffic counting information, providing us real-time information. We've got the Vivacity Labs cameras, which were deployed across the network. I think there was about 70 of those that we had access to. So they were giving us real-time data of motorised vehicle. We weren't interested in this particular project on pedal cycles and pedestrians, but that data was available to us. And then we had the Cloud Amber Common Database, which is Oxford's traffic common database, which was again providing us information. So we utilised Vivacity's API, and we used DataX2 and DataX1 feeds from those three systems. So that's giving us the real-time information on the traffic side, and then we have the real-time information on the weather and the air quality, as I've talked about in the last on the last slide. That goes into our integrated system, so the dispersion model and the traffic model. So the traffic model is providing these tailpipe emissions, and we're basically running that whole county-wide area in 2 or 3 minutes. And we were providing that into the dispersion model. The dispersion model was then running their simulation and then providing that back to us. So that's just doing the do nothing. That's exactly what's happening right now on the streets, but without any comparisons of different strategies. We then add another complex level of information. So response plans and strategies and customizable metric regions. So if we were to go back a couple of slides, and we're not going to, but if we did, one of those images, we actually defined KPI regions across the network. Specifically, we called out the A34 north to south, the A40 cross, the key corridors into the city centre itself, and the ring road areas. And then one other area that we pulled out was the air quality management area, specifically on the A34 at Botley Road, because that was one key area that always exceeds the national legal limits of NOx. So we really wanted to focus on that. Once we've got those KPI areas, we then defined some response plans, some traffic management strategies that would try to mitigate against hotspots of air quality. So what we actually thought when we started the project was that there was going to be lots of traffic management strategies that we could just automatically load in the system. But actually the first part of our realization was that until you actually have this system where you can actually start to see the impact of air quality and traffic together, then once you can see that, you start to realize, actually, I haven't got strategies that are fit for purpose. So we designed some in the offline environment in our transport model. We then loaded them up into the system, or the ones that were successful, we loaded up into the system, and then we could then play those through. So our real-time prediction engine is then comparing those different traffic management strategies in those customizable KPI regions to see which ones work best and which ones work best for the KPI regions, specifically looking at targeted areas. And that then gives us the ability to say, OK, is the base scenario do nothing, or decision 1, 2 or 3 a better one to actually invoke in the traffic management system? So all the way through this, it's all about informed decision making. And now we've got this data, we can start to see what we can actually do with it. So let's just talk about, next slide please, how this data is then used within the project and within the AQMA. So the next slide says use case 1, Kennington Bridge. So this is a bridge that's going to be reconstructed in the next 2 or 3 years. It's up for replacement. There's also some waterworks that are going on as well, some flood alleviation works that are going on at the same time. So it's actually quite a major construction for the area. In the consideration for this this bridge being reconstructed, obviously it's going to cause some traffic issues. So what is the alternative? Is the alternative to route people around a different way? Is it to have a contraflow? Or is it just to allow people just to find their way around the network through whichever roads are particularly open? So we looked at 3 different traffic management strategies, and then we played them in real time. So it's a bit artificial because actually the bridge wasn't closed, but we wanted to see what would happen if the bridge did close. Where would the traffic go and what would be the impact on emissions? So if we go through the next slide, we'll just flick through. There's a little bit of a build on this. So this is just 15 minutes. Let me just explain the slide first. What we've got on the left-hand side is we've got a do-nothing scenario. So you'll start to see that the traffic density builds up around the bridge closure area. And then on the right-hand side, we've got the contraflow, which was one of the traffic management strategies that we were comparing. So this is a contraflow. It's keeping one lane open in both directions. So 15 minutes, 30 minutes, 45 and 60 minutes, we're looking at an hour out just to see how that traffic builds. So Greg, if you can just pass through and then stop on 60 minutes. Great. So what you see is that if we just did the bridge closure, then the traffic density would really build up and cause some severe issues around the local area. It would also block it out onto the A34, so a key part of the SRN. This is a key route, especially for freight. It takes basically traffic from the southern ports all the way up to the Midlands. So it's a key arterial as far as the strategic road network. And so actually just a local road issue falling back onto the Highways England network is really something that we don't want to happen. Whereas on the right-hand side, if we can keep one lane running open, then you can see that the density of traffic is a lot less and the local conditions are much better. So this is really important, but actually keeping a contraflow open may well actually delay the construction or may cause the construction cost to be longer because you have to have that traffic management mitigation going all that time. So if we just go to the next slide, because this is really just about traffic density. So if we go to the next slide, and you can just fast forward on the build here, this is the dispersion model overlaid on that traffic, and you can start to see how the air quality then disperses from the road network across the local countryside. In all the slides and the analysis that we've looked, in all the images and the data that we've looked at, there is a west to east wind generally in the Oxfordshire area. And we see this actually across the country, but there is a west to east area. And so when we're looking at the A34, all the pollutants are effectively being blown towards the city centre. So when you start to see this data and visualize this data, you can start to think about, well, how do I then invent traffic management strategies that take into that weather considerations? But obviously, you can see from this image, it's now being blown towards the local road network, towards the towns, villages, and obviously the urban conurbations. So that shows you the power of the data being pulled together in one image. Next slide, please. We did 3 use cases in the project. The first one was that one. Another one that we did was closure of the M40. So what happens when the M40 is closed? Basically, the traffic jumps off the M40, it goes on the A40, it goes round the southern or northern bypass of Oxford and then joins the A34 and carries on. We did some analysis on that, but I'm not going to talk about that one today. I'm just going to go to the second use case that we're going to feature, which is the A34 Botley Road. And this one was specific because just where you see the Tesco's Express to the right-hand side, that is the air quality management area that regularly exceeds the annual legal limits. So what we did, next slide, is we investigated some different traffic management strategies, as I talked about earlier, in an offline environment, and we created a bunch of strategies that we could deploy, be it in the morning or the afternoon. Obviously, the flow of traffic is slightly different, so it's important to understand which part of the day that you're doing. And so the do nothing was one scenario that we're looking at. So no changes to the traffic management. And then others were divert traffic, gate the traffic, increase the green time, etc., etc. So traditional traffic management of traffic engineering tactics being deployed, but just being evaluated with this real-time data, real-time traffic data, real-time air quality data. Next slide. So as the project ended, we did an evaluation period, and this is ongoing. I'll come back to that before I finish my little update. So first off, how accurate were our predictions? Because if our predictions aren't accurate, then really the usefulness of this information is perhaps, or the system is not so good. So 76% of our predictions were within 15% tolerance of observed flows. So those from a traffic engineering principle, 15 minutes is pretty good for a dynamic model. And bearing in mind that this dynamic model happens to be a dynamic model that is being updated and being modified all the time because we're in this real-time environment. So that's so our predictions were comparable, and over time our predictions get better. What we've got is we've got some AI and machine learning that sits there in the back of the system that actually starts to learn and improve our predictions and our modelling outputs. Over the days evaluated, 57% of those days actually exceeded air quality legal thresholds. So 43% actually were under the legal limit, which is great. But actually it shows that we need to, so not every day is the same. And that's a real takeaway from this system. And it goes back to one of those early points that I made earlier. Those static models that are county-wide don't have that finesse or the difference between one day or another. And yet 57% of the days we exceeded the air quality, and each day was different. We do actually have, in a longer presentation, we have a version of and shows that the same detector on all the different days of the flow, it's different every day. So in this scenario, we were comparing the base case, do nothing, and 3 different strategies, and we compared them in the morning and the evening. So we did 2 sets of data. So in all of those evaluations, 65% a traffic management strategy that wasn't the base scenario, so wasn't the one that's actually invoked on street, mitigated against air quality. So it improved the situation as far as traffic and therefore improved air quality. So out of those 57% of those days, 65% of those days, we can do something. We can actually take action. And then if we did take action, how much would that benefit or improve? Well, it ranged from 2 to 20% on average. 2 to 20%, and it's 5% on average, and majority around the 3 to 6% mark. So that was an improvement or benefit was recorded. So really the whole system improved from end to end, that actually from predictions to evaluation where we exceeded to whether we can actually mitigate and what we can mitigate against, there was a benefit to the system. 2 things to note on the project: these are all model benefits. We're not going to say they're not, we're not going to overclaim what they are, but these are modelled benefits or simulated benefits. Oxfordshire County Council are now coding these different strategies into their UTMC, and then once they're done, we're going to do some end-to-end testing of to actually see them all the way through and then record the difference, because bear in mind we've got these Zephyrs deployed. We can now use those to see, once we've deployed the traffic management on the ground, whether we actually get a difference in the air quality. So we're going to do that. And obviously this was a limited project for reporting purposes and finances from our sponsor, Highways England. So we had to conclude the project at the end. But what we've done is we've kept the system running, and now we're still running those scripts every day. And so over the next 6 months, we will be, and now that traffic has actually improved, because this is really important, it's one thing I haven't said, this was all done during COVID times. So this evaluation was during October and November, when we were just between tier, we either had tier or we had a lockdown. Traffic was bouncing back at the start of the period, so traffic was all over the place. And our traffic management strategies were based on normal full occupancy of traffic. So now we're back to a normalised traffic where actually we're seeing normal traffic conditions. It's really important we do some more further evaluation. So we've got the next 6 months where we're going to be doing some more evaluation to be able to get these same, look at these same 4 questions, if you like, and see what our percentages analysis is going forward. So we will be doing an update, and I urge you to keep in contact with ourselves and Earthsense for updates as we go, and we'll do those in 3 months' time and 6 months' time, to give some further information. So that's it for me. Sorry, I've gone on a little bit too much. I'll hand back to Greg for the next stage.
Fantastic, thank you, Gav. Very insightful, very interesting overview there. I think we're coming back to Gary just to give us a summary of what the key takeaways and learnings have been from today's session. Over to you, Gary.
Yeah, thanks, Greg. So I think the key question now is, why have we done this, and what does that mean for a transport authority who is looking to improve the air quality in their town or city? And we've got a number of learnings from this project and the other projects that we've conducted around this as well. And the first is that transport authorities now are able to very cost effectively measure the air quality, which they can use then as data and evidence in policy decisions. No more do we have to rely on the odd base station to be able to make that decision on policy about whether we should be introducing a low emission zone, for example, or some other air quality policy. But now you're going to be able to have the sort of real data and evidence collected cost effectively through Zephyrs distributed. We can use that data and evidence gathered as well as traffic and air quality modelling tools. Transport authorities can set, measure and monitor air quality targets for developers. So it would be usual to set those targets as developments construction is undertaken. But perhaps now you could use the data produced as sort of evidence around the future target of air quality in a certain area, and possibly even incorporate those targets within traffic impact assessments. So rather than relying on the more traditional outputs of a traffic impact assessment, perhaps air quality and certain thresholds could form part of that assessment as well. Transport authorities now have the tools available to determine how transport network contributes to air quality problems. If we can measure on the ground cost effectively, especially in locations where we know that air quality, that poor air quality is generated, we can really collect that data to understand what impact traffic truly has and how we can mitigate that. Through air quality integrated traffic management systems, and transport authorities really have the tools available now to control and manage traffic, so that they can influence and have a positive influence on air quality. They're able to use traffic management systems now with air quality feeds to create simple or complex traffic management strategies very quickly. And they can enact them based on thresholds that they determine are the sort of mins and maximums for their particular town or city. And those traffic management strategies crucially can be tested before implementation. So as Gav was just saying there and showing, we can now use simulation software to simulate the impact of that of the traffic when you were to introduce a traffic management strategy. Perhaps we've done that before, but now you can link that to an air quality model. So not only are you testing the impact that the strategy will have on traffic and queuing and capacity, but now you're also able to determine what impact that new traffic pattern will have on air quality to really understand whether the implementation that you're intending is something that's going to be useful for your sort of given goals around improving air quality. We can now take a proactive approach to managing air quality as well, rather than the more simple approach and reacting when a certain threshold is reached. Using modelling software and really creating that digital twin, we're able to forecast or predict what traffic will be like in hours or maybe even days time, and then taking the feed from an air quality model, MyAir, then you can have a view of what the air quality might be like in a few hours time or a few days time. And that allows transport authorities to not necessarily react, but really be proactive and introduce traffic management strategies early. So rather than react when something happens, but perhaps even stop the situation from happening at all. If you know that on a particular day you might have particular air quality problems around the school, for example, you may be able to introduce some measures to actually prevent that from happening rather than dealing with it once it has happened. And perhaps we've managed to demonstrate as well now that there's a new success criteria that we can bring into traffic engineering, rather than relying on the more traditional measures of things like capacity, queuing and flow, maybe even journey time. But perhaps we should be introducing air quality as a demonstrable and quantifiable success measure And perhaps that's something that we should bring into our traffic management planning to not only focus on the more traditional, but look at how does air quality, how would this particular scheme impact air quality in that particular area. So these are the kinds of takeaways that we've got from this, and what we would like to do in the future. I hope you found what we've talked about today interesting. I hope we've given you some new ideas about how you might be able to manage traffic and air quality differently in your authority. Please get in touch with us if you'd like to know more. I'll hand back to Greg.
Thank you very much, Gary. That was excellent. Yeah, just to thank the speakers again for their time today. Thank you, Roland. Thank you, Gav and Gary. Very insightful, very interesting, and a fascinating project. And just to sort of emphasise what Gary said there, obviously, if there's any questions, please feel free to pop them into the chat now if you haven't done so already. I can see a couple starting to come through. We've got some time now before the end of the session to answer any questions, and again, feel free to reach out to us directly for any particular information that you might require for services we can offer. Contact details are on screen there. Please feel free to get in touch. Let's see, we're getting some questions. Questions just come in here from Chris at City Logic. With the likely change to the way people work and travel, is the AM/PM peak going to be the same post-COVID? If not, does this cause issues in the static model developed to date? How do we overcome? Probably a good one for Gav.
Yeah, thanks, Chris. I could always count on you on some good challenging questions. Well, firstly, I guess in this system that we're using, because it's a real time, we disregard almost the AM and the PM peak. We're covering the full 24 hours of the day. Certainly, what we've noticed through the analysis of the project is that the AM is pretty much the same level. It's just spread out a little bit more, but the PM peak just doesn't exist. It falls away. It never materialises. So what we put that down to is that people are still going, potentially going to work or dropping people off at school during the certain times. But they're not necessarily coming back at the same time. They're not coming. It's not the 9 to 5:30. So there's much more flexibility in the way people work. And I think that kind of does, that. So in the real-time system, we cover that. Actually, our predictions were less accurate in the afternoon, if I'm honest, as they were in the morning. But that just was, again, set up and the limiting time that we had within the project. And we would work on that as over time goes. So I think what it does is it actually does kind of, it does raise a big question, and it's a question that we're talking about at Modelling World International this afternoon, about the different trends, if you like, in modelling in the future. But yes, I think it definitely causes a question to look at the traditional static models. And how they're developed, and then how do we overcome? I mean, my answer is to how do we overcome? We have to look at much more dynamic models, and we have to look at much more time throughout the day, especially as the conversation right now is a Monday. A Monday is going to be very different than a Friday. Friday has always been 20% light because people don't go to work on a Friday, but it's going to be potentially even more so. The Friday might be the new Thursday, or the Thursday might be the new Friday. So we've got to understand that, definitely. So yeah, great question, and it's one that we're going to be talking about a long time. But yeah, that's the benefit of real-time modelling.
Thank you, Chris. Thank you, Gav. Another one to Gav here from Eric Linzus. What are the input parameters for the emissions model LEM? What makes it more accurate than the COPA FE? Okay,
I would have to get back to you offline because I don't know COPA FE. What I would say is, I'm not saying that it is as accurate as anything or as an alternative, and the reason I'm saying that is because the question is always going to be how accurate does it have to be able to give you an accurate answer versus a trade-off of it's accurate enough for the computational time that we have within this real-time situation. So bearing in mind when we've got a base scenario and 3 different comparisons, that's running 4 scenarios over a 15, 30, 45, 60 minute predicted window. So that's 16 different simulations that we have to do, and we try and turn that round in 10 minutes. And that's end to end, not only the traffic model, but also the dispersion model, and then evaluation, the KPIs, the outputs. So we're doing an awful lot of things in a very, very short time. So yes, we do trade off accuracy, but that's because of the speed. So computational time and software development will actually improve all of that as time goes by. But we feel that it's effective enough to give us an indication of the right direction for traffic management responses in relation to air quality.
Thank you, great question. Thanks, Gav. And then we'll come to Roland, I think, for 2 questions here from Stuart Snedden. First question is, interesting presentation. Thank you. Data quality is a concern with lower cost sensors for the Zephyr. How does the NO2 sensor response change over time? How do you know when ambient ozone starts to interfere? That's question 1.
Yeah, it's a nice question. We didn't spend much time on the data quality of the Zephyrs today. So Zephyrs generally have 7 microgram accuracy when they leave our reference station and are shipped to a customer, and those that we track across the UK on co-locations next to reference sites have accuracies of better than 10 micrograms for 12 months, even 18 months and more. So we are constantly tracking the performance of the fleet. It obviously does degrade over time. We think at least 18 months, maybe 2 years is a good life for an NO2 electrochem, and we are confident that they will provide good information in that timescale. Just interesting to think about the relative error bars. So our measurements are sort of 5 to 10, 7 to 10 micrograms for NO2. Our model is generally accurate to within 10 to 15 micrograms. So you're not too far off between the two, but the measurements are still more accurate than the modelling. But of course, the modelling gives you that forecasting and that wider view. So if we can get those error bars down to the 5 micrograms or so, it definitely will help the modelling and help the applications in due course. In terms of the ozone interference, our sensors do have electrochems for ozone and NO. We have deliberately put in the full suite of photostationary states so we can always check the ratios, check the patterns of those. And we do find that in very high ozone, you definitely get a peak in the NO2 electrochem. It does respond, but it's in the higher ozone levels, and generally finding that in very specific industrial locations. So we can measure that directly with the ozone signal, and we can respond to that, and we know how to do so. And so it does happen, but it's a relatively minor part of the NO2 signature, and it doesn't impact on that 10 microgram error in most situations.
Thank you, Roland. And a connected question from Stuart here. How does operating in winter mode and summer mode affect the correlation with reference measurements?
Thank you. So yeah, winter mode is a 1 minute sampling instead of 10-second sampling that is put in for those units on solar panels. So not relevant in this case because they were hardwired, which is great, but it is really useful for power management. Now, because reference measurements are hourly anyway, all comparisons end up being averaged up over quite a few measurements. And I would say it's statistically insignificant, the change in agreement with a reference monitor when you are 10-second versus 1 minute. You obviously have 6 times the independent measurements, but our individual operation of the sensor over that minute is optimized so that we don't lose any more signal to noise than we absolutely have to. So you're within a microgram or so of the error bar when you go to winter mode, when you go to 1 minute resolution. The challenge is the mobile applications, which normally you get GPS at 10-second, NO2 at 10-second. That's harder to do, but of course that's rarely on a solar panel. So relatively insignificant in terms of the switch to winter mode. In fact, most of our fleet is moving to 1 minute sampling just to make data management easier for our customers, because 10-second is rarely needed unless you're mobile.
Thank you, Roland. And I'll probably come to Gary for this one. It's from Matthew Langdon. How many spare cores are required at an LV and an ELV signal pole to power the mini Zephyr units, and what is the range of capture for them, i.e. how many would be required at a typical 4-arm junction?
So hopefully, I mean, a short answer, the number of cores is 2 spare cores at the pole cap, 2 in the controller. And then we have a 24-volt supply that's mounted on a panel that goes inside the cabinet attached to the swing frame. That's the same for it's designed to fit in any cabinet, any manufacturer traffic signal controller cabinet. In terms of the number, you would only need 1 at an intersection, one at one intersection. Whether you have them at every intersection will really depend on policy, and what we would do there is work with Earthsense to understand what density of sensors do you need within your town, sort of correlated to what policy you're trying to drive, and sort of how granular you need that data. But certainly you wouldn't need more than one at an installation, and possibly you wouldn't need one at every installation, maybe one every 100 meters of installation of traffic signals, but certainly not more than one at a single traffic signal site.
Thank you, Gary. Follow-on question here from Paul Taylor, probably for Gav. What defined the choice for LEM as a London model used in Oxford, and what effect did its use have on map air model validation, e.g. did it explain the initial overestimation before scaling?
So I think it's a two-part question. I'll try and answer the first one, and Roland might answer the second one. So I'm just giving him a heads up that I might like him to jump in. Thanks, Roland. I saw a slight nod on the head. The LEM model has been developed so that it can be used within a mesoscopic model rather than microscopic or macroscopic. So we've got three different types of scale, if you like, of model within our software. And we were using a mesoscopic model within the system, partly because of the scale of effectively the county and the area that we were covering. The fact that the LEM works on mesoscopic was pretty much the biggest choice. The second choice probably was the time, again the computational time, which I've talked about just a minute ago. And whilst we've got a couple of other emissions models within the software, this was felt to be the most up-to-date and relevant in the discussions within the project at the beginning. So that's the kind of the reason why we chose that one. Roland, do you want to talk about the overestimation for scaling? I'm not sure that's, I understand the question, but I'm not sure that's the right terms. Over to you.
So it's been a really interesting project for understanding the linkages between the measurements, the emission scenarios, the transport assumptions, and obviously lockdown has confounded a lot of what we wanted to do. So I think a lot of the lessons we'd want to learn are coming in the next 3 to 6 months as we return to normal patterns, because we've got a fantastically detailed emissions profile, varying emission profile. We've captured all of our ventilation coefficients so we can apply them in seconds across multiple scenarios, and we're now going to learn how that spatial pattern agrees in all the different wind conditions based on an emissions model that has some fantastic assumptions and detail behind it. We'll say assumptions, fantastic calculations and granularity behind it. So I think we will learn very, very neatly in the next 3 to 6 months how that goes. We had an initial overestimation. We found we had to correct our model in the first few months, but since then lockdown has come in, and responding to the different traffic patterns has been the priority. But over the next 3 to 6 months, we will see how the granularity of those emissions profiles down every single street enables us to understand the pattern around our 20-odd Zephyrs, and then the modelled dispersion assumptions to get us to the point where we gain confidence and more information on those emissions and how well they relate to the fleet and the driving behaviour and the start stop, etc., and how that relates to a measurement that might be 1 metre from the road versus 2 metres versus 3 metres versus in the middle between the carriageways on the lighting columns, etc. It's a fascinating data set that we're now gathering.
Thanks, gents. I think we've got time for probably a couple more questions. A question here from Adnan Uturul. Apologies if I've mispronounced the name. Is the traffic data coming in with detailed attributes, brackets, car types, emissions by car, EV, car? Are you combining this with sensor data, or are you purely adding the CO, NO data? Probably one for Roland, maybe a first stab.
Well, if I start the first part, Roland, is that all right?
Yep.
So basically the London's emissions model is basically taking the mixed vehicle fleet composition from London data, and then it's working that through. So the data classifications that we get from the traffic counters are effectively our cars, public transport and HGV, and that's the information that we're taking, and then we're basically applying that in the mixture of composition that's in the LEM to give the tailpipe emissions estimates, and I guess again it comes back to that the compromise between any more detail then if we have more categorizer vehicle classifications within the model, then the model is slower to then run, and therefore, actually, by the time we get a result, then the time has passed. So that's the trade-off, if you like, and that's why it's an indication towards traffic management strategies and the best one. So I think that probably answers the first part. Roland, do you want to add to that?
So that most of the answers are there. So in most of our models, we do all of that vehicle profile emissions based on emissions factor toolkit and the partitioning, but all of that was done by Aimsun here excellently. So we took that NOx emission, we partitioned that between NO2 and NO, thought a bit about the chemistry, and then obviously modeled the NO2 from there. But yeah, most of the vehicle fleet profiling was done by Aimsun in this case.
Great, lovely. I think we'll just take one more question, and Rodrigo Fernandez, I see, has asked a few questions. So if I can just cherry pick a couple from the list, and then we'll get back to you, Rodrigo, with answers to the remaining questions by way of follow-up. Coming to Roland for this one, what air pollutants do you model? Are particulates included?
So we do a PM 2.5 model. We had to optimize for one thing here, and we chose NO2, but optimizing for both PM 2.5 and NO2 is very, very possible indeed.
And in terms of the question, is it viable to establish city-scale air quality management and analysis without sensors based in air quality modelling tools only?
Yes, but you'll get less accuracy, of course. You want to tie them down, and as soon as you get to understanding moving traffic between one street and next and that operational adjustment of things, you really want the measurement points, because you have much larger uncertainties if you don't have measurements tying down your model.
And I'll just add to that, and it relates to the question above, which is, yes, we appreciate that our tailpipe emissions estimates or predictions are perhaps as less accurate than perhaps some people might envisage they were or like to have. But that's why we've got the KPIs is that combination of that plus the dispersion and the air quality sensors. So it's really a case of we're kind of validating, if you like, 2 or 3 times round to give us the best answer that we can get with the systems that we've got, which enables us to do that. We could do it on a citywide model just based on the traffic model, but would that be accurate or not? And it would just be one view of the system, and that's really why the combination of the two coming together gives us a much truer picture, which we feel comfortable with in making those recommendations to the traffic management officers.
Greg, can I just add in there as well that whilst that might be one of the limitations that we had on this particular project, we would definitely welcome working with somebody on another innovation project where we may be able to get the real-time traffic. I don't know, maybe through ANPR or some other sensor technology. So if anybody has a particular project in mind, then get in touch. We would definitely like to work on evolving this further and improving it further. And just one final thing on the citywide model. Whilst today we take the point data from the Zephyr into the traffic management system, again, a roadmap, we're looking at how do we get that full model data into the traffic management system. So you're not just relying on the point data from the sensor, although, as Roland says, if you want that extra quality and accuracy, then you would need a sensor there to give you that. But we sort of providing that redundancy through providing that model into the traffic management system as well. That's a future roadmap item that we're looking to do.
Yeah, that's a good point, Gary. Holistic capabilities there. And probably just one more question, which we'll take from Ian Hutt. Was the traffic model using data from the UTC so that it could react to real intraday changes in traffic plans costs? Probably for Gav, I'd suggest that one. And that'll be the last one for today.
Yeah, we were taking data from the 3 different data feeds. So Highways England, Cloud Amber, Vivacity. We were taking information every 5 minutes, every day during that whole period, and evaluating every 15 minutes, effectively the next hour forecast. And then under the evaluation period, we were just doing a morning and the afternoon evaluation. But that's purely just because the amount of data that we were creating and evaluating. But the system was there, and we could invoke an event and try it any time. So I could pop up a window now, see the real traffic on Oxfordshire's network, compare different strategies to see which one would be best, applying to the situation right now at any time of the day. So yes, completely. Good question. Thank you.
Wonderful. Great. Thank you again to the speakers. I think we'll leave it there in terms of questions. Thanks to the attendees today. Some very insightful questions there. Anybody we haven't answered, we'll get back to separately. And again, if anybody has any further questions that they didn't want to raise today, please feel free to get in touch with either of us or all of us, and we'll do our best to get back to you. And again, thanks very much. The recording will be distributed to those probably in the next sort of 24 hours or so. But thanks again to everybody, and yeah, have a good day.